Hello, this is the section 6.2 to 6.3 lesson. For this lesson, you want to print the z-score table contained in the lesson folder. We will be using this for both the lesson and the homework, and you'll also need it for quizzes and tests. Last chapter we introduced the idea of random variables, and we mentioned that there were two types, discrete and continuous. A discrete random variable, the values have to be of a certain type, like integers. Whereas with continuous random variables, they don't have to be of a certain type. They can take any value within some range without any gaps, interruptions, or jumps. Last chapter we talked about discrete random variables. In this chapter we're going to talk about continuous random variables. And like last chapter, we talked about different types of distributions for discrete random variables. This chapter we're going to talk about a couple of different types of distributions of continuous random variables. The first one we're going to talk about is the simplest. It's called the uniform distribution. A continuous random variable has a uniform distribution if its values spread evenly over the range of possibilities. Or in other terms, no value is any more or less likely than any other. The word uniform kind of means everything is the same, and that's the basic idea here. Everything has the same probability. So to illustrate this, let's suppose that a professor arranges his classes so that they always last between 50 and 52 minutes, never any shorter, never any longer. And suppose we went out and we measured the lengths of several of these classes, and we formed a histogram of those lengths. So we got maybe 100 or 200 different class lengths, and we formed a histogram. And here's what the histogram looks like. So notice on the horizontal axis we have class length that goes from 50 up to 52. On the vertical axis we have frequency. Now look at the shape of this histogram, or really the lack thereof. What we see is that all those bars are roughly the same height. All those frequencies are roughly 25, not exactly 25, some are a little shorter, some a little bit taller, but there's no real shape there. It's kind of flat on top. Well, that's kind of the basic idea behind uniform distribution. What we're seeing here is that all of these different class lengths between 50 and 52 minutes are equally likely. Well, there's a problem with a histogram like this, is that it makes it look like the class length has to be of a certain type. It makes it look like it has to be exactly 50.1 minutes, or 50.4 minutes, or 50.7 minutes, or so on and so forth. But that's not at all the case. Class lengths could take any value at all between 50 and 52. It doesn't have to go out to just one decimal point. So in other words, this histogram makes it look like the class length is a discrete random variable, when indeed it is a continuous random variable. So to solve this, what we're going to do is kind of smooth out the histogram by drawing a nice smooth curve on top of it that kind of has the same shape. And in this case, all our frequencies are about 25, so we're going to draw a curve there at a height of about 25. And so we're going to use this smooth curve to describe the distribution of these class lengths. Now this curve is what we generically called a density curve, and it's the graph of a continuous probability distribution. As we'll illustrate here in a bit, we're going to use this to calculate probabilities. So as our first example, let's let the random variable x equal the class length, and let's find the probability that x is greater than 51.5 minutes. Or in less technical terms, we want to find the probability that a randomly selected class lasts greater than 51.5 minutes. And so to do this, the first thing we do is we sketch the density curve. And on the right here we sketch the density curve without the histogram. We don't need those vertical bars in order to calculate probabilities. All we need is the actual curve. And so on the horizontal axis we've got, we call it the x-axis. It's labeled class length. The vertical axis we label it as p of x because the height of this curve is going to give us probabilities. And we see that the class length goes from 50 to 52 minutes. And the height of our curve is 0.5. Here in a minute we'll talk about why that height is 0.5. But right now we'll just take it for granted that that's equal to 0.5. Okay. So after we've sketched the density curve, the first thing we're going to do is go over to the number that we see inside of the parentheses and draw a vertical line. So we're going to go over to the number 51.5, draw a vertical line to the top of my density curve, And then the next step is I'm going to shade to either the left or the right of that vertical line depending on what values of x I'm interested in. In this case, I'm interested in x greater than 51.5, so we're going to shade to the right. And so we've got this shaded rectangle, and the area of that shaded rectangle equals the probability I'm interested in. This is what we mean by areas underneath the density curve are going to give us probabilities. So now we need to calculate this area. Well, we've got just a simple rectangle. Area of a rectangle is height times width. The height is 0.5. The width is the difference between 51.5 and 52, and that difference is 0.5. So width and height are both 0.5. So we multiply them to get 0.25. And so there's our probability. Okay. Now what that means in less technical terms is that means that 25% of our classes are going to last between 51.5 and 52 minutes. Now every density curve must satisfy these following two properties. There are many different types of density curves, but they all may look a little bit different, but they all have to satisfy these two properties. The first property is that the total area under the curve must equal 1. And the second is that the curve cannot fall below the x-axis. Now in last chapter we saw some properties that every distribution must satisfy, and these properties are somewhat similar, and they're analogous to the properties we saw there. The second property is true because the height of the curve gives us probabilities, and probabilities can't be negative. So if the curve falls below the x-axis, we'd have negative probabilities, and we can't have that. The first one is extremely important, and we're going to use it frequently. One thing this does for us is it explains why the height of our uniform density curve that we just saw is equal to 0.5. If we look at our density curve, it's a nice simple rectangle, and the width of that rectangle is 2 because the class always lasts between 50 and 52 minutes. So for the total area underneath that curve to equal 1, the height times the width has to equal 1, so that means the height has to be equal to 0.5 for the area to be 1. So that explains why the height of that curve is equal to 0.5. Now our second type of distribution we're going to talk about is one that we've already mentioned before. It's an extremely important distribution called the normal distribution. And remember back from earlier in the semester we said that normal distribution is synonymous with bell curve. Well, let's look at an example of this. Let's suppose we go out and we weighed a whole bunch of men. So we collected their weights in pounds, and we constructed a histogram of those weights. And let's say this is the histogram that we've constructed. So if we look at the shape of this histogram, we see that it starts low and increases to a maximum, and then it decreases down to a minimum again. So it's got a nice smooth bell curve shape. But notice that the weights here range between 120 and 240 pounds. With the way this histogram is constructed, it looks like the weights have to be either 120 pounds or 135 or 150 or so on and so forth. It looks like they have to be of a certain type. In other words, it makes it look like the random variable of weight is discrete. But in fact it's not. It's continuous. It could take on any value between 120 and 240 pounds. So to solve that problem, we're again going to solve it by drawing a nice smooth curve over the top of our histogram. And so in this case our smooth curve is this bell curve. And we see that this bell curve kind of goes through the tops of all those bars. Not exactly, but fairly close. Okay. Now, a simple equation that describes this bell curve is given here. Actually, this isn't so simple, it's actually rather complicated. Don't let this scare you because we're not actually going to use this equation. We just put it up here for illustrative purposes. That's some important properties there is that the curve is bell-shaped and symmetric. That's why it's called the bell curve. The mean mu is right in the middle. Remember, mu is the population mean. And it's symmetric, meaning that the left half of this bell curve is a mirror image of the right half. And again, areas underneath this curve are going to give us probabilities in the same basic way as areas underneath the uniform density curve gave us probabilities. So we just defined the normal distribution. Now to start off with, we're going to look at a special case of the normal distribution that's called the standard normal distribution. Standard normal distribution deals with the case where a population has mean mu equals 0 and standard deviation sigma equals 1. Now one reason that we talk about this special case is because the equation that describes the bell curve in this case is a little bit simpler than the more general case that we just talked about. That's given here. Notice it's still fairly scary, so we're not going to be using it, but it is a little bit simpler. The corresponding density curve is shown there. Notice again it has the bell curve shape. The area underneath that bell curve is 0. Notice that 0 is right in the middle because that's the population mean. But notice that we've labeled our horizontal axis as z-score rather than x value, and you'll see why we do that here in a bit. To illustrate one use of the standard normal distribution, let's consider this scenario. The Precision Scientific Instrument Company manufactures thermometers that are supposed to give readings of 0 degrees Celsius at the freezing point of water. Tests on a large sample of these instruments reveal that at the freezing point of water, some thermometers give readings below 0, denoted by negative numbers, and some give readings above 0, denoted by positive numbers. Assume that the mean reading is 0 degrees Celsius and the standard deviation of the readings is 1 degree Celsius. Also assume that the readings are normally distributed. Okay, so let's take a step back and talk about what's going on here. So we've got these thermometers. 0 degrees Celsius is defined to be the freezing point of water. And so at the freezing point of water, a thermometer should read 0 degrees Celsius. But thermometers aren't perfect. Sometimes they're going to read a little bit high, sometimes they're going to read a little bit low. So we went out, we tested a whole bunch of these thermometers, and for each one of those we recorded the measurement at the freezing point of water, and so that gave us a whole bunch of different data values. We calculated the mean of those values. We got a mean of 0, calculated the standard deviation, got a value of 1, and we constructed a histogram of those values and saw that it looked kind of like a bell curve. So that means they are described by a normal distribution. So we have here a population with mean 0, standard deviation 1, and a normal distribution. So we're dealing with a standard normal distribution. So we're going to be able to use that bell curve that we just talked about in order to calculate probabilities. So to illustrate how to do that, let's look at this question. If one thermometer is randomly selected, find the probability that, at the freezing point of water, the reading is less than 1.58 degrees. So to calculate this, we're going to start off setting it up the way we did those uniform distribution problems. We're first going to define the random variable. In this case, we're going to call it z, and z denotes the reading. Now when we deal with standard normal distributions, we always use the random variable z. So in mathematical notation, I want to find the probability that z is less than 1.58. So to do this, the first step is to sketch our density curve. And so we know what our density curve looks like. It's a bell curve. It's got 0 right in the middle. Now your picture does not have to be real pretty, just has to have the basic shape, and the important thing is that 0 is right in the middle. So now we're going to go over to 1.58 and draw a vertical line. Now exactly where 1.58 isn't terribly important, just as long as it's somewhere to the right of 0. So now we're going to shade to either the left or the right of that vertical line. In this case, we're interested in z less than 1.58, so we're going to shade to the area to the left. And so the area of this green shaded region is the probability that I want. Okay. Now, this area is not a nice simple rectangle like it was in the uniform distribution. And so calculating this probability, this area, is not going to be as simple as taking width times height. And in fact, calculating this area is very complicated. And so to simplify things, we're going to use this z-score table. And there's two parts to this table. There's a positive z-score side and a negative z-score side. And if you look at the upper left-hand corner, you see this bell curve and an area shaded. To the left is some z-score. This z-score table gives us areas to the left of z-scores. And you see there the title is Cumulative Area from the Left. Now the way we read this is the left-hand column contains the first two digits of the z-score, and the top row contains the last digit. And so in this case, we've got a z-score of 1.58, And so we're going to go down to 1.5. We're going to go over to the column labeled 0.08. And the number inside the table is our area, 0.9429. Okay. So that's the area to the left of z equal 1.58. That's our area, and that's our probability. Okay. So our probability that z is less than 1.58 equals 0.9429. Now we should always take a step back and ask ourselves, what does this mean? Well, what this means informally is that if we were to randomly select many different thermometers, then about 94% of them would read less than 1.58 at the freezing point of water. We can always think of probabilities in terms of percentages of our population. Now let's look at another example that's going to be very similar but with some different numbers. If one thermometer is randomly selected, find the probability that at the freezing point of water the reading is greater than negative 1.23. So in mathematical notation, we want to find the probability that z is greater than negative 1.23. We'll follow the same basic steps. We'll sketch our density curve. It's the exact same density curve we just used. We're going to go over to negative 1.23 and draw a vertical line. Again, exactly where you draw negative 1.23 doesn't really matter, just as long as it's somewhere to the left of 0. Now in this case we're going to shade to the right of that number because we're interested in z greater than negative 1.23. And we need to find that area. So to find the area, we're going to go to our z-score table. We're going to use the negative z-score side. And we're going to go down to negative 1.2 and then over to the column labeled 0.03. And that number there, 0.1093, is the area to the left of negative 1.23. So if we go back to our picture, that number we just found is the area to the left. So that's the area of the unshaded region. Well, I'm not interested in that unshaded region. I'm interested in the shaded region. And so to find the area of that shaded region, I can use the fact that the total area underneath the density curve must be exactly 1. So if the total area is 1, then that means the area of the shaded region has to be 1 minus the area of the unshaded region. So 1 minus 0.1093 is 0.9807, and that's our probability. Okay. Now, what does that probability mean? Well, if we were to select many different thermometers, then about 89% of them would read greater than negative 1.23 at the freezing point of water. Now let's look at a fourth example that's going to involve two numbers here. If one thermometer is randomly selected, find the probability that at the freezing point of water the reading is between negative 2 degrees and 1.5 degrees. So in mathematical notation, we want to find the probability that z is greater than negative 1.2 but less than 1.5. Now don't let the fact that we're dealing with two numbers here scare you. We're going to approach this in the same basic way. We're going to sketch our density curve. Now in this case we're going to draw vertical lines at both numbers that we see inside the parentheses. So we draw them at negative 2 and positive 1.5. Now in this case we're going to shade in between those two numbers because we're interested in values of z between negative 2 and 1.5. So the area of that shaded region is the area that I want. So to find that area, we're going to have to do a little bit more work than we did in the previous examples. First, we're going to go to our z-score table and look up z equals negative 2.00, and we'll find that the area to the left is 0.0228. Now that's not the area that I want, but we're going to have to use that. Now next, we'll go to our positive z-score table and look up z equals 1.50. And we'll find that the area to the left is 0.9332. Now that's not the area that I want either because that starts at 1.5 and goes all the way to the left. I don't want to go all the way to the left. I want to stop at z equals negative 2. So to find that area that I actually want, I need to subtract those two areas. I'm going to take the large area, subtract the small area, and I get 0.9104, and that's the probability. Okay, so we just talked about the standard normal distribution. Now we're going to talk about a generalization of this. And to illustrate it, let's look at this example. Adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. find the probability that a randomly selected adult has an IQ that's less than 130. Now, at first glance, this problem may look very similar to what we just did because we're dealing with a normal distribution. However, note that this is not a standard normal distribution problem, and that's because we have a mean of 100 and a standard deviation of 15. Remember, a standard normal distribution dealt with the case where we had a mean of 0 and a standard deviation of 1. When we do not have that case, we call it a non-standard normal distribution problem. Now, we're still going to be using bell curves to calculate probabilities, but there's going to be one additional step here. So to calculate this, we're first going to define our random variable. In this case, we're going to let it be x. It equals the IQ score. Now we're using x here because we are not working with a standard normal distribution. It's a non-standard normal distribution. We only use z when we talk about the standard normal distribution. So in mathematical notation, I want to find the probability that x is less than 130. Okay. Now, before we start drawing our bell curve, the first thing we need to do is convert this x value over to a z-score. And we're going to use this formula here, z equals x minus mu divided by sigma. Now, this is the same formula that we used back in Chapter 3 when we first introduced the idea of z-scores. Okay. So in this case, x is 130, mu is 100, sigma is 15. And so we do that arithmetic, z comes out to be 2. Now, what does that do for us? Well, the probability that x is less than 130 then equals the probability that z is less than 2. Well, now what's the benefit of that? Well, when we work with z, that means we're working with a standard normal distribution. So now this problem here, the probability that z is less than 2, is a problem that we just did, or just like a problem that we just did. So to find that probability, we're going to sketch our standard normal density curve. So that's our bell curve with mu equals 0 right in the middle. We're going to go over to z equals 2, draw a vertical line. We're going to shade to the left because we're interested in z less than 2. Then we're going to go to our positive z-score table, look up z equals 2.00, and we'll find that the area to the left is 0.9772. And so there's my probability. Probability that x is less than 130 equals 0.9772. Now, what does that mean? Well, that means if we were to randomly select many different people, then about 97% of them would have an IQ less than 130. So we see that working with these non-standard normal distribution problems is very, very similar to working with a standard normal distribution problem. We just have one additional step of converting the x value over to a z-score. So that's it for the section 6.2 lesson. The homework is titled section 6.2 to 6.3.